what we have seen so far, it's a case in which we assume that the density is constant. But that's just simplification, just to make it easy now to explain things. But in reality, that's not going to be the case. In reality, density is going to be a variable. And how are you going to measure density in practice? Anyone knows? You guys took Professor Torres Berlin class? Yes? No? So what tool do you use in order to measure density?
Neutron density.
Well, yeah, neutron density is mostly for water. But to measure bulk density, you use gamma density, the gamma density tool. All right, so what we're going to do now is to find the equations that allow us to calculate vertical stress when density is not a constant. All right, and for that, we're going to solve a very simple problem of statics, in which we're going to consider a cube with a weight and that cube with that weight, we're going to put it also into a coordinate system. Let me check the coordinate system. It should be this. And in that cube, which is going to be in some place in the subsurface, we're going to have a stress applied on it. I'm drawing just one arrow, but it means many arrows. Remember that stress is force divided by area. And let me draw the hidden side of the cube. This one is acting on the top. On the bottom, I'm going to have the same stress I have on the top, but actually I'm going to have a little bit more, because is that little bit more the amount that I need in order to balance the weight. Okay? So if you multiply this one and this one are going to be the same when they are very small. So this is that additional amount. All right. So as you used to do in statics, what do you do in order to make sure that a body is not moving? You do summation of forces, and in this case, you're going to do in direction z equal to 0. And that means that this is not going to move in direction z. All right, so we're just simply going to do that. First, we're going to start with the stress which is going up, which is positive, which is this one. And if this is stress, what do you think I should multiply for?
Area.
An area, right? So the area, the size of this cube is delta x in this direction, delta y in this direction, and delta z. So here I'm going to multiply times the area, which is delta x, times delta y. And to that, I'm going to add the forces which are going the other direction. And this one is going to be SV, and that one is also applied on the same area, delta x, delta y, and mg. And all of that should be equal to 0. Okay, before we move to the next step, let's simplify something. this one, SV times delta x delta y, is the same as that, negative SV delta x delta y, right? So we're going to cancel that out. And therefore, we're just going to have on this left-hand side this amount, and I'm going to take it out of the parentheses, so it's like that. And this one, I'm going to put it on the right-hand side, and it's going to be a positive quantity. What is m in this case? M is the mass of the cube, right? But let me convert that to something without units of mass, but instead of terms of density. So the mass is going to be equal to what? To density times volume, right? And what is the volume of this cube? It's simply delta x, delta y, delta z, right? And then I have g over here, and we see that these two things appear on both sides, and I can cancel them out. And what this tells me is that the equation that we were looking for, that the variation of total vertical stress with depth is equal to the density of the rock times g. And this is what is called the total vertical stress gradient. Why is it called a gradient? Because that means it's the amount that varies as a function of depth. So this is valid just for a very small point, okay? So I can generalize now this for a real rock and say that the variation of vertical stress with depth is going to be a function of the density that now is going to be a variable. And I'm going to take it into the rock terminology, assuming that we have pores and we have fluids, and this one is a function of z times g. G is not a function of z, right? We assume it constant. So what would you do now if you wanted to know SV at a given location? So this it's a differential, very simple differential equation. If this is a derivative, what do we do in order to get rid of a derivative? You integrate, right? So we're going to integrate this. We're going to move this dc on the other side, and I'm going to do the integral of this part from 0 to z. And let me change that in a bit. This one goes from 0 to z, density bulk, z, g, and this is from SV at z. And we're going to further assume that the total vertical stress is 0 on the top at z equal to 0. So I'm already making that assumption over there. So the final result is going to be that the integral of 1 is just SV. SV as a function of depth is the integral of the bulk density times g. That's it. That's all you need to compute vertical stress when the density is a variable. So now with this equation, we're going to be able to, if we have a given location with different kinds of rocks, let's say here a carbonate, a shale, a sandstone, and anything, here we're going to be able to now calculate the stress as a function of depth. Okay? Did you guys wear your orange? I see just one I didn't. One orange. Friday you're supposed to use orange, right? That's what our president wants. Okay, so I was talking about now if density is a variable, it doesn't matter how much it varies, we still are going to be able to tell what is the vertical stress with this equation. All right, so what is an integral in geometrical terms, especially an integral, I forgot something here. So remember that this one goes over there. An integral with respect to depth, so this is the variable, this is what we are integrating on. What is going to be the integral here in geometrical terms? It's going to be, starts with A, area. The area of the function underneath the function. That's the integral. So, for example, when we were computing before with a constant stress, let me take the onshore case. The equation was simply density bulk, which is this value, times G times Z, is the area of this rectangle. It's just the area. When we go into the onshore case, we have density water G times C water, which is the area of this rectangle, plus density bulk G times C minus C water, and now C minus C water is the distance from here to there, so it is the area of this rectangle. It's just the area. Don't forget the G though, but it's just the area. And in the same case now, when we go to a case that varies with depth, it's just going to be the area. Okay? So, how are you going to do this now in a file that you have 10,000 entries of density? So in some of those files, you're going to have density every, say, 1 foot. Okay? All you have to do is just add up. No, this is too tall for me. Okay. All that you have to do is just add up the areas of those rectangles at those points. Okay? And SV, if you compute it numerically, is just going to be the summation of a value of density bulk at a position, well, let me do it with Zi plus the value of density bulk at Ci plus 1 times G times delta Ci from I that goes from 0 to the position n. So let me zoom in here. So I'm missing something here. This is going to be the average. So in each of these, let me do a case in which, let's say that we get over here. Let me vary this linearly. The area of a trapezoid is equal to the base times the average of the two heights. And this is basically what you see over here. The average of the two heights times G times the base is going to give you the contribution of that part. So even if all of those densities are different, you can still calculate what is the value of SV. And that's what you have to do in the homework. Okay? First, there is a sort of more or less an easy case. Let me come back over here. Let me know, guys, if you have any question, okay? All right, so here, this is a case with a few entries, about 20, but you have to do exactly the same to what we discussed. You have depth, you have density, you add all those areas, and you calculate SV. Later on, we have to do something else, what we're going to talk about now, to calculate pore pressure, but don't worry about that. The other case here is with a file that has lots of entries. So you need to read this file. You don't want to do this manually, right? You do it with Excel, you do it with Python or anything. But for every depth, so here in the first track, you're going to have depth, which is that value, and then you have density, and with depth and density, you can do the exact same thing that we did before, with some additional thing, but we'll talk about that in a little bit. Okay. Everything okay so far? Any question? No? Let me emphasize again that this calculation of total vertical stress is very important, okay? I'm going to ask you to do this in the homework for a real case, but you should know how to use also simplified calculation, because we're going to do that a lot.